Now let's have a couple of examples on the indirect boundary element method. Both of these are going to be exterior problems. The first one is just a theoretical problem, sort of an idealized transmission, and the second is an actual problem that has been experimentally verified of a beaded plate. Our first problem is an automobile transmission. We looked at this earlier, so we've already seen the geometry. This time we'll use the indirect boundary element method, and we will have the vibrating surface that radiates a noise, and then we'll view that noise on a cylinder a meter in diameter that's centered on the transmission. We're going to do a frequency response problem here, and this particular model has already been analyzed for frequency response using MSC Nastran, and we know the surface velocities as a function of frequency, and those reside in a set of tables. We'll have to bring that information into our Comet acoustic run. We're going to find the sound pressure level then out on a cylindrical viewing surface that surrounds this body and is aligned with the transmission axis. We used this same physical example in an earlier lecture on the direct boundary element method, but I'll repeat a lot of the details here so that you have an idea of the physical problem. Here is the transmission housing. It's modeled with plate elements. It has openings at the back here and the front, which normally allow connection to other shafts and gears and so on. But for our purposes, we're going to close that at both faces. We're going to assume that that's a rigid boundary and doesn't enter into the vibration of the body and the production of the sound. Our current method, the indirect boundary element method, would allow us to model certain fins on this body due to perhaps cooling fins or lugs that are used for mounting, because we now can handle those free edge conditions. But we don't have such ribs in the model. It's a simple model, and so we don't exploit that capability. Now for our boundary element modeling, we're going to close the ends of the transmission and thereby create a single zone for this indirect boundary element model. Also, we have the freedom to choose arbitrarily the sign convention for the element normals. But since we've done this before as a direct boundary element model, and since we might in the future want to return to that, we'll choose the same sign convention as for the direct method, which was that the element normals point away from the acoustic domain. And so in our case, to be consistent with the direct method, we will choose our element normals to point toward the center of the transmission. Now we'll look at the solution procedure, and this will parallel the information given in the Comet Acoustics Examples Manual. The items on this page are presumed to have been done at the time we start describing the problem, so this is a bit of a review of the introductory work that has been done. First of all, the acoustic boundary element model has already been calculated in a general purpose finite element program such as IDEAS and written out as a universal file. The mechanical frequency response has been calculated in MSC Nastran and put out in punch file format under the sort 1 option -1. Now this is good for our work because it takes at a given frequency all the nodal data presented in column form. If you do it in a different format, it sprinkles the frequency results around in a way that's harder to recover. So at the present time, I believe that this is a default for the if you leave it out, but it's good to call this out explicitly. Then we import that acoustic model into Comet Vision, decide on the various views that we would like to see. We define and save whatever element groups that we're interested in, certainly the one for velocity interpolation that includes the moving surfaces around the transmission case. We define a data recovery mesh, which in this case will be a cylindrical mesh centered on the axis of the transmission, and we have assigned the material properties of the air. The serious work of the example now starts. We use Comet Vision to handle this process. First of all, we need to interpolate the velocities from this structural model and get that into the acoustic model. These are the commands that are done in a command sense. This is more easily done with version 3.0 and onward in the Comet Vision program. But there are certain result sources we name. We look at our structural model, and the results ask for all the cases. So generally I would follow the example manual for Comet on this set of instructions and do it graphically. It's terribly boring to do that here in this format. You have to look at a lot of screen images. Anyway, you set the analysis parameters and checking and so on. You write your Comet Acoustics data deck coming out of Comet Vision, then you run Comet Acoustics and then post-process. So it is a bit cookbooky here, and now we'll go into the results next. Now let's look at the results. We'll start out by looking at the mesh that have been used in setting the problem up. The larger exterior mesh shown here is the viewing surface, which is a cylinder 1 meter in radius, centered on the same axis as the transmission. Then the finer mesh is the actual boundary element mesh on the surface of the transmission. The most interesting result of this example is the pressure field viewed on the viewing surface. Here's a pretty color contour plot of the decibel level for sound pressure. We're seeing that the vibration of the transmission, which is hidden a bit here because of the hidden line removal, causes maximum sound in this area over in here, more or less adjacent to the most highly vibrating part of the transmission case. We're going to look at the frequency response and plot it as a function of frequency for a node right here, number 764. So it's one of the warmer spots, you might say, at this end of the transmission, which is actually the end away from the engine. Let me show you a view of what the screen on a workstation would look like when you're using Comet Vision for post-processing. Here we see the amplitude part of a conventional frequency response curve. Frequency is plotted along the horizontal axis, and then the sound pressure level in decibels on the vertical axis. This is the perceived sound pressure level at the viewing surface at node 754, and notice that there are effectively two rather major resonant points here. You'll recall that the original mechanical excitation was due to an unbalance in a rotating shaft within the transmission that was mechanically transmitted through the bearing support to the walls of the transmission case, which vibrated, and then transmitted through the air as sound. In the next figure, I'll show a Postscript version of the information that can be obtained through this Comet Vision plot. It's a little cleaner here. and again showing the resonant points that I had discussed. Let's see the frequencies there, something on the order of 230 hertz there, and on the order of 380 there. So you have to watch the logarithmic scale, but clearly if you wanted to reduce the noise at that point on the viewing surface at node 754, you would want to work on these frequency ranges here, which would contain the bulk of the energy. The second example that we'll consider is a beaded plate. This example is based on an experiment that was done at one of the big three auto manufacturers in Detroit. Basically, it was a plate that might represent a floor pan, let's say, in an automobile. The beads were parallel corrugations in the plate. The plate was clamped around the four boundaries. The free area, free to vibrate, was roughly 16 inches square. An excitation was provided toward one corner, and then acoustical measurements were made at a distance from the plate on a viewing surface. Here's a picture showing the beaded area in the center, and then these radiating lines here represent the clamped area. So the actual situation then is a plate that has some clamping fixture around its edges, as I'm sketching, which then is vibrated by a load. And it's a frequency response problem in general, but we'll consider one specific vibration frequency just to concentrate our effort. The model itself will involve the beaded area, plus it will involve the extension out into the clamps, and the total model is flat as shown here. So the details of the clamp are not modeled. That would have some minor effect, but basically the sound pressure coming off the bottom of the panel is free to migrate around in free space and then be measured above the panel. And so you have definitely an interesting problem, and one where the indirect method is a valuable method for solution. The basic information for input into this problem outside of the geometry consists of the measured surface velocities that were experimentally found. And so this problem has been rather well conditioned, bringing information forward to compare with by theory. So the surface velocities were experimentally measured and put in an ASTRAN punch file format. Those were read into Comet Acoustics, and from that then we have the velocity boundary conditions needed to calculate pressures at any point in the field. Those are to be compared then with the measured sound pressure levels, and that figure will show that later, and actually comes out to be fairly good in comparison. Now, in the physical modeling, I've got some structural ideas here. They're not really important in the sense that the measured surface velocity characterizes the plate condition. But it is a thin plate, and the Kirchhoff-Love plate theory would hold. You'd expect the vibrations to be small enough to be in the linear range, both structurally and acoustically. We're going to assume a clamp boundary condition, and that affects the way we set up the acoustic model, though, because we need that clamped region to be stationary. And we know, in fact, that you can never get a perfect clamp in an experiment, but we're just going to assume that that has happened. Our beaded plate is presumed to be vibrating out in open space. Of course, there are some fixtures nearby and some remote walls. Here's the cross-section of the plate, and the fixed regions will be at the outer edges of the plate where it's clamped in the fixture. But sound can propagate out around the edge of the plate from one side to the other. We'll place a viewing plane on one side of the plate to recover our pressure results. The indirect boundary element method will be used. We're going to use quadrilateral elements. We're going to use a variational formulation, and that will yield symmetric matrices. We'll apply the zero pressure jump at these cut edges of the plate. This will be interesting because we'll have a zero pressure jump right at the edge of the plate, and then there will be a short region that will have a zero lateral velocity imposed, and then the interior part of the body will be elastically vibrating. Let's run through the procedural steps in getting a solution. We'll assume that there are 3 data sets that have already been obtained in preliminary work, and those involve the boundary element model itself, which has been created in MSC Patran and output in a MSC Nastran bulk data file. Now, of course, Patran doesn't have boundary elements in it, but it has all the shapes and the connectivities that are needed. The data recovery mesh is also created in Patran. This is written out in a Patran neutral file format. Then the velocities at the surface of the plate are put into a Nastran punch file format. Now we go into our acoustic solution. We'll import the acoustic model into Comet Vision first. In our solution process, the next thing to think about is whether there are these unusual conditions, namely junctions between multiple plate components or free edges. In our case, we do have free edges, and we need free edge constraints to be set by typing this. We could also at this point have taken care of the multiple junctions and causing constraints to make the proper pressure jumps there. We define and save our desired views, top, 3/4, and so on. Define our group for velocity interpolation, and that would be the exposed center area of the plate, the beaded area. We interpolate our velocities from the structural model results, which are really the measured results, and put those onto the acoustic model. Assign our air properties, pretty much standard sea level properties. Set our analysis parameters and checking parameters. Write out the Comet Acoustics data set. We then run the Comet Acoustics program, and then we can post-process back in Comet Vision. I'll show you the mesh that's been developed now. Here is the plate mesh, and these would be quadrilateral plate elements in a top view, and then an oblique view here. You can see the beaded portion a little better in this lower picture. And you can see the region that will be clamped then in our model with zero velocity around the 4 sides. When you have a free edge or a cut edge on sheet material like this, then you want to tame that pressure difference at that point, and that's done with so-called free edge constraints. These can be set in the Comet Vision program. The nodes in question are called out as these red circled nodes, so it's easy to see where the free edge constraints are being applied. Now let me show the velocity field that has been imposed on this problem. Here's the velocity due to the point load that's vibrating the plate. It's vibrating the beaded plate. The contact point is off in this corner. The exact point is not available to me because it hasn't been provided by the experimentalists. I guess for a lowly damped system it wouldn't matter so much. If there were high damping, you'd want to know exactly where that was. In any event, we show here a kind of a velocity boundary condition with arrows that is probably not as good as a fringe plot, which is also available, shown in the next figure. Here are the fringe plots of velocity as well as the phase of the velocity field. And this is a little more easy to comprehend. These are the amplitudes above and then the phase angle below. Phase angles go from minus 180 to plus 180 degrees. And so the plot here is a fairly rich plot of the phase relation among the various parts of this oscillating plate. Let's look at our theoretical results now. Given that experimentally measured velocity field on the beaded plate, then using Comet acoustics we have developed a predicted theoretical sound pressure level on the viewing plane. The plate is shown above here and the viewing plane below. Notice that the pattern is not symmetric because of the way the load was applied off toward one side. The sound pressures are as high as 75 decibels, and remember this was at one frequency, 942 hertz. We're using the standard reference pressure of 20 micropascals. The measurements were taken at that viewing plane in the experiment, and now I'll show those nodes in question. There's a grid of 3 by 3 shown here, so there are some 9 microphones laid out. The spacing on this mesh is an inch by inch pattern. Therefore, there are some measurements given here, and these really are in inches. The viewing plane is about 14 inches below the surface of the beaded plate. So there's a certain amount of averaging then that would take place down on the viewing plane from the different phasing of the portions of the beaded plate. And that's a thing that's not obvious and would be hard to predict with classical methods. I'll show a close-up of those same measurement points. And here they are in this portion of the plate. So they really extend over some rather noisy areas and then some quieter areas. In our last figure, we'll compare tabular values of the predicted and the measured sound levels. Those 9 points have their coordinates laid out here. And as we'd mentioned, they range from fairly noisy down to fairly quiet. This is getting close to a standard office level of noise. And the correlation is pretty good, especially at these higher levels, which are the important ones, where the energy is. And notice that these are really quite close between measured and theoretical values. The third highest here, so the top 3 points are really in good agreement. When you get down to the quieter areas, then the agreement falls off a bit. But you see that's a zero crossing idea that always comes out in experimental data, that when you've got something that's becoming small, it's harder to control the error in that. So it could be a combination of experiment and theoretical differences there due to experimental error or theoretical modeling assumptions. All told, I think we'd have to pronounce this comparison between experiment and theory as a great success, and shows that there is some possibility now to do significant numerical acoustic studies in the practical industrial situations.